So here is the code. I'll explain you the code, right? So these are the header files we are defining, right? And here we are defining an structure, and this structure contains only one variable key. Okay. For this structure, we are creating a user-defined data type, which is called as element. Okay. Now you can create like for an element, you can create variables. Okay, right? So the initial capacity of the queue is set as 2. It is a circular queue. So I guess you are remembering that in a circular queue, one location will be always kept empty. Okay, one position will be always empty in a circular queue. So even though the capacity is 2, it can hold only one element. It cannot hold two elements. Okay, we are creating two pointers for element. One is q, the other one is new q. Okay, one is q, the other one is new q. And initially the rear and the front pointers were set to 0. And this is the logic for checking whether the queue is empty or not. Here we just check that if front is equal to rear, then the queue is empty. So we return 1, otherwise we return 0. For checking whether the queue is full or not, so if you recollect again the, let me show you the queue. Okay. See, I have drawn two queues because two cases we are going to discuss. So what is these two queues? What are the two cases that I will explain later? So this is case 1 and this is case 2. Okay. But before that, in a generic queue, when the queue is empty, I mean in a normal circular queue, when the queue is empty, what will be the value of front and rear? Front and rear both will be 0, right? Front and rear both will be 0. Okay. When the queue is full, okay, when the queue is full, what will be front and what will be rear? Assume there is no deletion happened in the queue. Assume that no deletion happened in the queue. Okay, when the circular queue is full, what will be the value of the front and what will be the value of the rear? Yes. Front is equal to 0, that is fine. Rear is equal to what? Rear is equal to what? When the queue is full, what will be the value of rear? N minus 1. Good 169. That is correct. N is size. Okay. So rear will be size minus 1. Okay. Rear will be size minus 1. Right. If I try to insert one more item into this queue, okay. If I try to insert one more item into this queue, when the queue is already full, okay, then what will happen to rear? Because before inserting, we have to check. Yeah, rear will become 0. Okay, then you have to check. So first you have to increment rear and then you have to check whether front and rear is 0. If after incrementing, if they become same, I mean if rear is becomes equal to front, then it means that the queue is full. Okay, so that in the full logic, first we are incrementing rear. Of course, as it is a circular queue, we are doing modulo capacity. And then we check if rear is equal to front, return 1. It means that the queue is full. Otherwise, return 0. Okay. And this is the logic to copy the contents from one queue to another queue. We'll come to this later, or I'll tell briefly what it does. There are 3 pointers: start, end. Start says from which location you want to copy. End says up to which location you want to copy. Okay. But we are not going to copy up to end. We are going to copy only up to end minus 1. Okay. If it is end, it will copy up to end minus 1. And destination says what is the destination location, what is the address of the destination location, or where it is to be copied. And just here we run a for loop. ITR is again is a pointer to element. All these parameters are also pointer to element. So for ITR equal to start and I is equal to 0, while ITR less than end, here we are not saying less than or equal to end, less than end. Okay, so it will not go up to end, it will go up to one level which is less than end, right? ITR plus plus I plus plus. Here what we are doing, destination refers to the location where the things to be copied. Okay, so destination plus I is initially 0. So whatever the destination address, there the starting ITR will be initially stored. That first value will be copied. Okay. So here value in the sense actually it is the ITR is a pointer, right? So ITR is a pointer to element. So it holds some address. It holds some address. Okay. So that will, so wherever ITR is pointing, okay, that will be copied here. Okay. And then we are saying moving percentage D to new queue. Whatever we are moving, we are saying that. Like that, it will copy all the elements starting from start to end minus 1, right? And this is the logic which will be called when the queue is full. Whenever the queue is filled, whenever the queue becomes full, you have to double the queue size. So we are declaring a variable start. And then we say that doubling the queue capacity from percentage D to percentage D. Okay, that is from capacity to capacity into 2. Like that, we are doubling the queue size. And here we are allocating space. The new queue, the queue with the extra size will be pointed by a pointer called new queue. So new queue is equal to element store malloc 2 into capacity into size of element. Okay. Previously, whatever the value of capacity, twice that much memory we are allocating, and that memory will be pointed by new queue. Okay. Right. Now the queue, there are two cases here, so that I have drawn this diagram. Case one is you have just inserted into the queue, no deletion has happened. Never you have did any deletion. You have just inserted into the queue and the queue becomes full. Okay. In that case, okay, here the queue size is 11. Here the queue size is 11. Okay. In that case, what will be the value of front and what will be the value of rear? If no deletion was performed in this queue, okay, but only insertion was done, and finally at one point, yeah, front is equal to 0, rear is equal to 10. Yeah, that's correct, Orion. This is the second case. In the second case, actually there are two deletions happened. I mean, removal should always happen in the front end. Okay, so two items were removed. 2 is removed and 4 is also removed. Okay, and later, after removing this also, the queue becomes filled. So in the second case, what will be the value of front and what will be the value of rear? In this second case, case 2, what will be the value of your front is 2, rear is, what is the value? Why 10? Why 10? No, rear insertion happens at rear end. Finally everything was, I mean, the queue becomes filled. If front is 2, then rear will be what? If queue is filled, rear is equal to 1. Yeah, that's correct. Front is 2 and rear is equal to 1. Okay, that is this case. Okay, right. Yeah, Akila, that's correct. Front is 2, rear is 1. Okay. Initially, when the queue was empty, what is front and what is rear? Originally, before starting, when the queue is empty, what is front and what is rear? When the queue was empty, what? Yeah, 0, 0. That's correct. Yeah, front and rear both will be 0. Okay. So when the queue is empty, front is also 0 and rear is also 0. Both were pointing to the 0th location. Okay, fine. So while copying, while doubling the size of the queue, you have to know whether it is case 1 or case 2, because for case 1 you have to, the copying you have to do in a different way, and for case 2 you have to do the copying in a different way, because we are doubling the queue size, right? So whatever the contents in the original queue should be copied into this new queue. Okay, so we should know whether it is case 1 or case 2. Case 1 means no deletion has happened. Case 2 means a deletion has happened. So how do we know that whether deletion has happened or not happened? How do we know that? Okay, uh, is there any idea? So for that, what we do here is, here we calculate something called a start. start is equal to front plus 1 percentage capacity. Okay, assume that our queue, in our queue no item was deleted. Okay, no item was deleted. In this case, what will be start? Start is equal to front plus 1 modulo capacity. So in that case, what will be start? Yes. So if you want, I'll write here start. We are calculating start is a variable of type integer. Okay, start is equal to, assume that the queue is full, not 0 kilo. Start is equal to front plus 1. Front plus 1 modulo capacity. Yeah, it is 1. 236, that is correct. It is 1. Because front is 0, 0 plus 1 is 1. 1 modulo, the size is 11. Capacity is 11. Okay. Current capacity is 11. Still, we are not updated the capacity. Okay. So 1 modulo 11 is equal to 1. Right. Okay. Fine. Then what we check? Then what we check, in the sense, if you go to the code, it is if start less than 2. If start less than 2, so less than 2, there is only one possible value. What is that? Because front is 0, then less than 2 means that it is only 1. Okay, so if start is less than 2, that is if, or you can also write here if start is equal to 1. Okay, then this case will execute. So this is for what? This is for which case? This is for which case? No deletion. Yeah, correct. This is for no deletion. In case of no deletion, what you have to copy? You have to copy everything. You have to copy everything, the whatever the queue contains, from the beginning of the queue to the end of the queue. Okay, that is, you have to copy from here to here. Okay, here to here you have to copy. Let us assume this address is 2000. Okay, let us assume this address is 2000. Okay, so all these are integer values. So if this is 2000, then this will be what? If this is 2000, then this will be what? 2004. Yes, yes, yes. Even though it is of type element, element contains only one thing, that is integer. So it is 2004. Okay, so we have to copy starting from wherever the front is pointing plus 1 to that location to wherever rear is pointing. Okay, to wherever rear is pointing, that much you have to copy. Okay, so what we are doing is, here we are calling the copy q plus start, copy q plus start, and q plus start plus capacity minus 1. What is q plus start? See, q is a pointer. Again, q is a pointer. It points to the starting address of the queue. Q is a pointer which points to the starting address of the queue. So basically, what is the starting address of the queue? This is 2004. Sorry. What's the starting address of the queue? 2000, not 2004. No, Aryan. Q starts with 0, right? This is this entry, right? Okay, this is array. Basically, this is an array. For our convenience, we are seeing as a circular array. So Q is actually referring to 2000. Okay, and here what we are doing, Q plus start. Q plus start. What is in start? Currently, what is in start? Start contains what? Start contains what? Previously, yeah, 1. Yeah, 1. So what is 2000 plus 1? This is address. You are adding address. So scale factor you should include. So 2000 plus 1, not 2001 Akila, it is 2004. Okay, scale factor is 4, right? It's address, right? So it is 2004. So starting, then it means starting from location 2004. So the first address is 2004. Okay, then what's the second address? Q plus start plus capacity minus 1. Okay, so again do the same thing. What is Q? 2000. Okay, Q is 2000. What is start? Start is, what is start? Start is what? 1. Yeah. What is capacity? Capacity of this array? 11. Capacity minus 1. 11 minus 1. Okay, so basically this is 11 minus 1, 10. Okay, and 10 plus 1, 11. So it is 2000 plus 11. So what is the resultant value you will get? 2000 2044. Yeah, so you will get 2044 including the scale factor, you will get 2044. Okay, so you can check, probably 2044 will be the address of the last entry. Okay, I mean 2044 will be the address of the, yeah, let us check what is 2044. It will see after 10 it is not 0. This is only for our reference. In the array after 10, there will be some address, right? So this is 2004. This is what? 8. Okay. This is 12. This is 16. This is 20. This is 24. This is 28. This is 32. This is 36. This is 40. Okay. Where is 44? This is actually in memory. This is in linear way or in circular way. That's what my question is. Here for our convenience we are keeping it circular, but actually in memory this is a linear allocation or a circular allocation. Linear, yes, linear. Okay, so actually it is referring to 2044. 2044. The end address, if you see, it is 2044. But our copy function will copy up to what? Our copy function will not go up to end. It will go to end minus 1. Okay, so end minus 1 means it will copy only up to what? 2040. Yeah, it will copy only up to 2040. Okay, so that is what that particular logic does. Okay, so it is q plus dot q plus dot comma q plus dot plus capacity minus 1 comma new q. Okay, so new q, for example, if new q's address is 5000, if new queue's address is 5000, starting address is 5000, then starting from 5000 all these entries will be copied. First, second, third, everything will be copied one by one, starting from this entry to this entry, it will be copied. Okay, so this is for case 1 when there is no deletion happened. This is case 2. Assume that 2 elements were deleted. Already 2 elements were deleted, that is 2 and 4 were deleted. Okay, so in where previously whatever was in 2, there 4096 is stored. Okay, and previously 0 was empty, there 2048 was stored. Okay, and currently this location is empty, the index location 2 is empty, and front is pointing here and rear is pointing here. Now also the queue is full. Okay, but now we will copy 2 times. In the first copying, what we will copy? During the first copy, we will copy from which element to which element? Yes. During the first copy, we will copy from which element to which element? Starting from front plus 1 to max minus 1. Yeah, Aryan, that is what? Element is what? 8 to 1024, right? Yes, up to this you will copy. Okay. During the second copy, what you will copy? The remaining leftover, whatever that you will copy. That is this 2048 and 4096. This you have to copy separately. Okay, right? So in the resultant queue, this 8 6 will 8, it will come in this order. That is the correct order. It is supposed to come in that order. 8, because that is the front of the queue, right? 8 16 32, it will copy up to 1024. Okay, after that it should copy 2048 and whatever the remaining 2048 and 4096. Okay, so this logic you have to write. Okay, so that in the else part we are writing uh, two copy statements. The first copy statement, what it does, q plus start. Okay, right? Now what is q? See, in this case, what is start? First let us calculate start. When there is no deletion, start was 1. Here what will be start? Start is equal to front plus 1 modulo capacity. Here what will be start? Yeah, start will be 3 because front is 2. Okay, front is 2. 2 plus 1 is 3. 3 modulo capacity, that is 11 is 3. Okay. So yeah, that's correct. Start is 3. Okay. So if you see the first statement, it is Q plus start. So what is Q and what is start? So Q plus start means what? In this, Q is always pointing to the starting address of the queue. So what is the starting address? Yeah, 2000 plus 3, that is 2012. Yes, Orion, that's correct. Yeah. So I guess others are following. So yeah, what 236 wrote, that is exactly correct. 2000 plus 3 into 4. Okay. So that is how we got that 2012. Okay. So I mean, here the queue is always pointing to the starting address of the queue, which is 2000, and in our case start is 3. Okay, and the scale factor is 4. So 2 plus 3 into 4, which is nothing but 2012. Okay. And what is 2012? Which location is 2012? If you refer this diagram, this 8, this is 2012, this is 2012. Okay, starting from here we are going to copy to where? To this up to this 10th location, I mean 10th index, we have to copy. So for that, what we are using here, Q plus capacity. Again, what is Q and what is capacity? What is Q, what is capacity? Q contains starting address. What is the starting address? What is the starting address? Yes, 2000. Yeah, what is capacity? What is capacity? 11. Okay, so 2000 plus 11, what you get? 2044. Yeah, 2044 you get. But always it will copy only up to the end minus 1. So what is end minus 1? 2040. Okay. So it will copy from 8 to this 1024, it will copy. In the new array, 8 to 1024 is copied. Okay. In the next round, we have to copy the remaining rest over. For that, what we are writing is, we are writing another copy statement, copy Q. Starting is Q. So what is Q? Q is referring to which address? Q always refers to the starting address. So what is the address? 2000. Yes. Then Q plus rear plus 1. What is rear? What is rear now? 2 is 2000. What is rear now? Rear is now pointing to which location? I mean, which index? 1. Yeah. So Q plus rear plus 1 is what? 2000 plus 2. So that is what? With scale factor, what you will get? 2008. Yes. So which is 2008? So as per this diagram, you can see this is 2008. This location is 2008. So it will always copy up to end minus 1. So up to which location it will copy? It won't copy up to 2008. It will copy up to 2004. Yes, good. So it will copy from 2000 to 2004. This is 2000. Zeroth location is 2000, and it will copy, even though you are giving up to 2008, actually the for loop goes less than n. So it copies up to 2004. So the remaining 2048 and 2000 and 4096 will be copied in the new array. Okay. I mean new queue. Okay. Right. Now this new queue is the double the size of the old queue. That is, it has a capacity of up to holding 22 elements. Okay, previous queue can hold only 20 elements. I mean 11 elements. I mean 11 minus 1 element. Okay, this is 22 minus, it can hold 22 minus 1 elements. So now where should front point? So as per this new queue, where the front should point? Where the front pointer should point? See, front will always point where? Just before the first element. Okay, front will always point to the recently deleted element. Okay, that is fine. Other way, what you can say, front will always point to the element which is before the first element. What is the first element here? What is the first element? 8. So 8 is at which index location? In this array, 8 is at which index location? No, index, array index. In this new array, I'm asking. New Q. No, as per C style, 0. It is in 0. Okay, right? So where will you make the front to point? This Q, this new Q's capacity is what? This new Q's capacity is what? 22. Okay. So when you perform front plus 1, when you perform front plus 1, modulo, what you call, modulo size, you should get this. Okay, you should get this. Yeah, exactly. So front should be 21. Okay, front should be 21. That is nothing but what? Capacity minus 1 or new capacity minus 1. Okay, that is nothing but new capacity minus 1. Or you can say in terms of old capacity, how you can say this 21? In terms of old capacity, how you can define this 21? Old capacity is what? 11, not n minus 1. Old capacity is 11. Yeah, capacity into 2 minus 1. Exactly. Capacity into 2 minus 1. Okay, right? So that here we say what? Front is equal to 2 into capacity minus 1. Okay. So that we say front is equal to 2 into capacity minus 1. Right? Okay. Now where the rear should point? Rear should point where? Rear should point, where the rear should point? See, with respect to old Q, where the rear should point? Old Q's capacity is 11. Okay. So that Q is full. So that you are going for the new Q. Okay. So with respect to that, where the rear should point? Are you getting? Old Q's capacity was 11. Okay. As that was full, so that we are going for the new Q. Okay. In the new Q, where the rear should point? Yeah, 10. But how you got that 10? Define in terms of old Q's capacity. We want generalization to code, right? This 10 capacity minus 1. Good. That's what I'm expecting. So rear is equal to, actually it is capacity minus 2. Okay, capacity minus 2. Uh, because rear, where it will, rear will point, okay, it is, for example, in this diagram, when the Q is full, rear is pointing here. Okay. So rear is equal to, its capacity is 11, 2 empty places. No, why 2 empty places? Rear will always point to which element? Rear will always point to the lost element of the queue. Rear will always point to the lost element of the queue. Okay, so it is, Oh, yes, this is just because of C style. Okay, just because of C style. See, 10th location is what? See, the location is 10th means in C, how we will refer? Location is 10th means 9. Yeah, because of that. Okay. But capacity we will say as 11. Okay, capacity we will say as 11. So 11 minus 2 will give that 9th location. Okay. So that we say this. Okay, nothing else, right? And then capacity should be multiplied by 2. Capacity equal to capacity into 2. And then what should we do? We should free the space for the old Q. Okay. And we call the new Q as old Q. Okay. And we say that Q is equal to new Q. Now, whatever the new Q, that will be renamed as Q. That is, Q is pointing to this. Okay. This is how we double the size of the Q. Okay. And this is just to display that Q is empty, right? And this is to add an element to the Q. So before adding, we check whether the Q is full or not. Okay. This, if it is full, okay. If the Q is full, then we double the capacity and then we increment the rear. Okay. See, here I have one question. If the queue is full, then we double the capacity and increase the rear. Otherwise, we are not incrementing rear. Why? Could you say the reason? What's the reason? Is the question is clear? If the queue is full, we are doubling the capacity of the queue by calling queue full. Then we are incrementing rear. Otherwise, here, why we are not incrementing the rear? Yes. Because is full what it does. If you recollect, yeah, correct. 236. That is exactly correct. Because that function is full itself, it will itself will increment. Okay. So this function, if you recollect, is full. It first increments and then only it checks. Okay. So already rear is incremented. Okay. If it is not full, then you have to just store. Okay. If it is full, then the rear pointer is pointing to the last element which is recently inserted, right? Then you have to increment the rear and then add the element. Okay. And this is the logic for deleting. Okay. If the queue is empty, you cannot delete. So if empty is equal to 0, it means that queue is not empty. Then delete. Deletion happens from the front end. Okay. Front will always point to the element which is just before the first element. So increment the front and show the deleted element. Okay. And then yeah, and then remove that element E and then display that. Okay. And update the front pointer. So with this itself, front pointer got updated. Just take that element and display it. So this is the main program. So here we are creating initially whatever the capacity, that much capacity, that much memory we are allocating for the pointer Q. Okay. Where each element is of where each item is of type element. So I think initial capacity is 2. Yeah, which means only one item can be inserted. Okay. And then for I is equal to 1, I less than or equal to 5, we are trying to insert 5 items, but you cannot insert more than one item. So the queue will double. Okay. So the queue will double, right? And again, we are actually inserting 5 items. We are removing all the 5 items using delete queue, right? So that's the logic. Let me check. Make underscore q dot slash. Okay, so this is the output. Think you understand this? Fine. Okay. So coming to today's session, coming to today's, the assignment, what I want you to do is, first is, I want you to implement the uh, doubly circular linked list. Okay. So first thing is you have to implement doubly circular linked list. You have discussed singly circular linked list. So you have to write the logic for doubly circular linked list. Okay. So create a doubly circular linked list, perform insertion and deletion, and display. Okay, all those things, right? Linked list. Okay. And the next thing is to write the deletion logic for binary search tree. Okay. So we have discussed binary search tree. We have discussed how to insert and how to search, all those things, but you should include the logic for deleting a node from a BST, binary search tree. Okay. So there are three cases which we have discussed. I guess you remember. If the node you want to delete is a leaf node, just delete that node. Okay. If X you want to delete, just delete X. Then you identify the parent of X and you identify what is X, whether X is a left child of the parent or the right child of the parent. If X is the right child of the parent, then its right child will be null. Okay. Its right pointer, that is its right child, I'm calling it as RC of the parent, will be null. Okay. Suppose if X is the left child, uh, then uh, then also same, identify the node X and locate its parent, then delete X, that is free up the space for X, and then make its the parent's left child pointer to point to null. Okay. So this is case one, that is if the node to be deleted is a leaf node. Okay. If the node to be deleted is not a leaf node, there is a, say there is a node, this is the node X you want to delete, that X has one child, okay. Say it is child 1. Okay, C1, but there is only one child. Okay. Then also you identify the parent of X. Okay. And then what you have to delete X, and this child should become what? Child should become which child of parent? Is it left child or right child? Right child. Why right child? Why not left child? Why is it right child? Is it because CH1 is the right of X? Is it because of that or what? Because what? Because for which reason? No, not that. It's not CH1 is the right of uh, the node you are deleting, not because of that. That's what I want you to understand. CH1 can be either here or here. Okay. Why we are bringing CH1 to the right of P? Yes. No, no, left child. No, see, this case 2 is only one child. Okay, left child is not filled. How do you know whether it is filled or not? See, you are talking about P's left child, 236. We don't know. Okay, CH1 is greater than P. Fine. Okay, anything else? Yeah, that's correct to a certain extent, but anything else? Case 2, there is only one child. See, there is, you need not check with CH1. You have to, X is what? X is P is what child? X is P is what child? Right child. Okay. So whatever, yeah, X is P is right child. So when you delete X, whatever the child of X, that should come to the right of P. That's it. It is okay. Don't go anywhere beyond. Okay. As X is the right child, and as you are deleting X, move this CH here. Okay. You can do like this also. Just move this CH here and delete this node. Okay. And this CH will not point anywhere, right? Further. Okay. Fine. Suppose if CH is the left child, suppose if CH is the, sorry, if X is the left child of P, and now there is one child CH, okay, it can be either right or left. Now CH will become which child of P? Left child. Yes. Why? Why? Why left child? What's the reason? Why it's left child? Why not right? because x is to the left of p. Yeah, because x is to the left of p. That is the reason. Okay, this is case 2. This is case 2. Okay, right. Yes, that is the reason. And case 3 is when there are two child nodes. Okay, so this is the parent node. Okay, and x you want to delete. X you want to delete, but x has two child, or you can, it can have a child subtree. Okay, so it can be even a tree. That's none of our business. Okay, we are not bothered about that, right? So it has two childs, ch1 and ch2. Okay, so now if you want to delete x, then what should you do? What is the process for deleting x? Yes, ch2 to replace x. Why? No, you have to identify the, you have to, no, 236. Actually, we have discussed this in the class. You should identify what? You should identify something. You should identify the right side of the node. No, you have to identify, yeah, infix successor. Yeah, exactly, Orion, that's correct. You have to identify the infix successor of x. And what will be the infix successor of x? What will be the infix successor of x? In the right subtree, whichever is the node with the minimum value, not ch2. Yeah, the least value in the right subtree. Okay, you have to locate the node which is the least value in the right subtree. And where will you find that? Where will you find that least value? Leftmost of which node? That's what I'm asking. Leftmost of Yeah, Shivamani, leftmost of which node? ch2. Good. Leftmost of ch2. So whichever is in the leftmost of ch2, that node you have to locate. Okay, say that node is some y. Okay, so what should, so then x will become what? X will become y. This will become y. This will become y. Okay, and now you have to delete y. Now you have to delete y. How will you delete y? Again, how will you delete y now? Again, what you have to check? What's the logic for deleting anything? Deleting, there are three cases. What are the three cases? What are the three cases for deletion? Yes. What are the three cases for deletion? Yeah, leaf node, one child and two child. Okay, so now see, when there are two child for a node, you have to identify the uh, infix successor. Infix successor is nothing but the smallest node of the right subtree. Identify that node, and whatever its key value, copy that to the node which you want to delete. Okay, that means you have changed this. So it means already it is as if this is deleted. Okay, that is fine. But now this y you have to delete. So again you have to check. Again you have to check whether y is a leaf node or not. If it is a leaf node, just delete it and make its parent to point to null, whether the parent's left pointer or right pointer, depending on this node. Okay, probably it will be left pointer, right? If it has one child, then make its parent to point that child. If it has two child, suppose y has two child, then what will you do? Suppose y has two child, say ych1 and ych2. Again same thing. That is, what is the same thing? Again you have to find the infix successor of y. Okay, and identify that and copy. Okay, so this should be done in a recursive fashion. Okay, so actually deletion logic you can write as a recursive algorithm. You can write as a recursive algorithm. Okay, I'll try to show you the algorithm, not the uh, okay. Yeah, give me 2 minutes time. I'm coming back. Okay, let us stop here. See that logic you have to find out, but I will give you the structure. I will give you the structure in the as a part of the question in the okay, as a part of the assignment question. I will give you the structure for deleting, like what are the three cases and how it is going to call recursively. That part also I will give something like an algorithm, right? And you have to develop it, right? Okay. So the deadline will be Saturday morning, right? And next week we'll have next quiz, right? Monday. You can start filling up the Google form.